Hi, good evening. This is my presentation for evidence number two, modeling control of a differential robot. Let's start. First, what is a differential robot? A differential robot is a type of mobile robot characterized by its method of movement, which is controlled through two separately driven wheels, usually mounted on the same axis. The key components, or the key characteristics are the following. First, the actuators. We are using in this case DC motors. The primary actuators in differential robots are DC motors, one for each wheel. These motors are responsible for the independent rotation of the wheels, which allows the robot to execute various maneuvers, like turning and moving in a straight line. Then we have some parameters like the wheel radius, which is denoted by an R. The radius of the wheels directly impacts the robot's movement. A larger radius increases the speed but may reduce maneuverability. While a smaller radius can enhance control at the cost of speed. Then we have the distance between wheels, which is denoted by L, or is also called track width. This is the distance between the centers of the two wheels, which is crucial for farmers as it affects the turning radius and overall agility of the robot. A wider distance makes for a larger turning radius but can offer more stability, whereas a narrower distance allows for a tighter turns but might reduce stability. Then we have the movement control. The differential drive mechanism allows the robot to move forward and backward by rotating both wheels at the same speed in the same or opposite directions, respectively. To turn, the wheels are rotated at different speeds or in opposite directions. This differential rotation creates a turning effect, with the robot rotating about a point along the axis between the wheels. We have different applications. Differential robots are popular for various applications due to their simple design and ease of control. They are used in industrial automation, robotic cleaners, and as platform for research and educational purposes. About the behavior, here we have the the transfer function that was provided to us. This DC motor transfer function represents the relationship between the input voltage and the output angular velocity. The simplified transfer function abstracts the motor's electrical characteristics like resistance and inductance, and mechanical properties like the rotor inertia and friction. In a more detailed model, uh, the let's see here, like the second model, um, the DC motor dynamics are typically represented by differential equations leading to this transfer function. Here, R and L are the resistance and the inductance of the motor coil, Y, J is the rotor inertia, B is the friction constant, and K is the motor's torque constant. This detailed model takes into account the armature coil's electrical dynamics and the mechanical dynamics of the rotor. Uh, for the PID controller, we're implementing PID controllers for each motor with specific gains, being KP, being the proportional gain 6.3, the integral gain being 1 over 0.06, and being the derivative gain 0. These controllers regulate the motor's speed to minimize the error between desired and actual speeds. The general form of a PID controller can be seen here, and this formula adjusts the motor's input or the voltage based on the proportional, integral, and derivative terms calculated from the error signal being ET. Our model uses kinematic equations to describe the robot's motion. Here we can see, the derivative of x, of y, and the derivative of our direction or angle. Here, omega r and omega l are the angular velocities of the right and left wheels, and r is the radius of the wheel, being here 0.05 meters, and l is the distance between the wheels, 0.25 meters. These equations relate the wheel speed to the robot's linear and angular velocities, crucial for planning and controlling its movement. In a broader context, the kinematic model for a differential drive robot, or a DDR, can be described as following. And this equation allows for various linear and angular velocities by independently controlling each wheel's speeds. Here we have the resulting graphs, both for x and y position and for our direction. In the context of our differential robot model, x and y can be interpreted as the coordinate positions of the robot in a plane, representing its location in a two-dimensional space. The variable theta, on the other hand, represents the robot's orientation or direction. It indicates the angle at which the robot is facing, which is crucial for understanding its heading and for calculating its future trajectory based on its current orientation. Here we can see that our x position goes from 0, increments a little bit, and then goes down until -5. Then our y position goes from 0 down until it reaches around -8. And we can see the direction changes just a little bit. It goes from 0 to around 2, and it stays that way. We can assume the direction it doesn't change that much compared to our position in our coordinate positions. Then we have our proposed model. First, we have, well, the transfer function. It represents the dynamics of the DC motors driving the robot's wheels. And the numerator, in this case 0.356, corresponds to the motor's torque constant, translating electrical input into mechanical output. Yeah. The denominator's coefficient 0.085 and 1 encapsulates the motor's electrical time constant, which is related to the inductance, and mechanical time constant related to friction and inertia. This simplified representation, while not capturing every nuance or every characteristic of the motor behavior, provides a practical and efficient means to simulate motor response to control inputs. Then we have our PID controller. The PID controllers have been tuned for each motor, which suggests a robust approach to achieving precise speed control. We have the proportional gain, which is at 6.3, and indicates a moderately aggressive response to the error, which is suitable for systems requiring quick adjustments. The integral gain, KI, is designed to eliminate steady-state errors, ensuring that the robot accurately tracks its intended path over time. The absence of derivative gain over derivative term, which in this case is, well, KD equals 0, suggests that the model might not prioritize mitigating rapid changes in error, possibly because the system's dynamics don't exhibit significant overshoot or oscillations. Then we have our kinematic equations for x, y, and or our direction. These equations are very important as they link the wheel speeds to the robot's spatial coordinates. The cos of theta and the sine of theta terms in the equations for x and y ensure that the robot's movement aligns with its orientation, and which is a critical aspect for accurate path following. And also the use of R and L, which is the wheel radius and the distance between wheels, directly in these equations indicates an approach that tightly couples the robot's physical dimensions with its movements, enabling precise calculation in its trajectory. Then we have here in this part, the integration. Well, here, I'm sorry, I forgot to explain. Here we have the PID controller with its corresponding gains, and here is the implementation. When we have already done the PID controller for both motors, we have its implementation with the kinematic equations to obtain the derivative for x, y, and the direction. After we have that, we make an integration of the derivative, and integrating the derivatives of x, y, and theta helps to accumulate the robot's displacement over time. This is important for tasks like navigation and mapping, where the robot's history of movements influences its future trajectory, or all its future actions. Well, here we can see the final analysis or the final results. Here is like a combination of both X and Y mapping that was done before. From that, we can use them both to create like an XY mapping of the robot. It's almost like if you're seeing the robot behavior from above, and we can see how he is moving through a map, and we can see that it's the same position as when we were seeing the individual positions. It starts from 0 and goes down until it reaches an X position of 5 and a Y position of around -8. And we can see that the direction of the robot or the angle of movement doesn't change that much. It's a small turn in the system. And we cannot see that this very clearly, but if we make like a zoom in our system or in our graph, we can see it's a little wavy. Well, this is because of the PID controller. It's not a perfect straight line, or it's not a perfect system, but it works. So we can see that it waves a little bit. It's correcting itself. It's diminishing the error between our desired path and the actual path. So it will be a little wavy. And for our final conclusions, we can say that the model is a good representation of a differential robot. It combines theoretical aspects of control systems with practical considerations of robot kinematics. It shows an understanding of how individual components like motors, controllers, kinematics interact with a robotic system. In real-world applications such as autonomous navigation or task-oriented robotics, this model will likely exhibit a good degree of accuracy in path following and maneuverability. The PID controllers, which are done for the specific dynamics of the motors, will ensure responsive and stable control. Future iterations of the model might include the addition of a derivative term in the PID controller to better handle rapid changes in error, or a more detailed motor model that accounts for nonlinearities and saturation effects. Additionally, we can integrate sensor feedback like encoders or gyroscopes which could further enhance the model's accuracy and robustness. And that will be all. Thank you so much. And here are my references. Thank you again.